Can you think of a math puzzle so confusing that even Isaac Newton had trouble solving it? That's the three-body problem. A celestial riddle where adding a third object makes orbits go from predictable paths to chaotic dances in space. Despite many years of trying, mathematicians haven't found a simple answer for it. Let's explore the mysteries of this tricky problem. We'll look at early attempts to solve it and use modern computers to simulate what happens when gravity meets the complexities of real-world physics. In 1687, Isaac Newton's Principia changed our understanding of physics forever. Newton's equations of motion and gravity turned our universe from unpredictable chaos into a clockwork of predictability. Using these equations, you could theoretically predict the positions of planets at any time, past or future, if only two bodies were involved and no other forces interfered. However, add just one more body and things get complicated. This is known as the three-body problem, unsolved for over 300 years. Newton's laws provide differential equations that, in some cases, can be solved with calculus to get a straightforward equation. Input the starting positions, velocities, and time, and you get the system's state. For two bodies, these equations give paths like circles or ellipses for orbits. These are conic sections, shapes like slices of a cone. Johannes Kepler even described elliptical orbits before Newton. But with three bodies or more, chaos usually reigns, and a simple solution remains elusive. After Isaac Newton's Principia was published, many mathematicians aimed to find simple, exact solutions for more complex systems, such as those involving three gravitating bodies. However, the influence of even a single additional body made finding such solutions impossible. This quest became an obsession for mathematicians. Yet, over 3 centuries, very few general analytic solutions were discovered. In the late 1800s, Ernst Bruns and Henri Poincaré convincingly argued that a universal analytic solution does not exist. The reality of the three-body problem is that most starting configurations evolve chaotically. Small changes in initial conditions lead to vastly different future states, resulting in unpredictable orbits that often lead to one body being ejected from the system. Despite these challenges, predicting the gravitational motion of multiple bodies has been crucial for tasks like nautical navigation over the centuries, and is now essential for space travel. How do we manage it? While a general analytical solution for the three-body problem is largely impractical, approximate solutions are achievable. For instance, when bodies are sufficiently distant, we can treat a many-body system as a series of simpler two-body systems. Each planet in our solar system, for example, can be approximated as orbiting the Sun in a simple elliptical path, akin to Kepler's predictions. However, these orbits gradually change due to gravitational interactions between planets. Another useful approximation arises when one of the three bodies in a system has significantly less mass compared to the others. In such cases, we can disregard the small body's gravitational effect and simplify the problem to the two larger bodies orbiting each other, known as the reduced three-body problem. This method works well for scenarios like artificial satellites orbiting Earth, or for approximating the Moon's orbit around Earth, considering the Sun's influence, or even Earth's orbit in relation to the Sun and Jupiter. While these approximations are helpful, they are not perfect. Even small bodies contribute to gravitational forces, and our solar system involves numerous massive objects. For instance, just considering the Sun, Jupiter, and Saturn creates a three-body system without a straightforward analytic solution, even before including Earth. However, the lack of an analytic solution does not mean there's no solution at all. To accurately predict the behavior of most three-body systems, we divide their motion into smaller segments and solve them individually. By breaking down trajectories into tiny steps or segments, we can use exact analytical solutions for each piece, such as straight lines or sections of two-body orbits around the system's center of mass, while assuming other bodies remain fixed. This approach, known as numerical integration, involves solving differential equations step by step. Applied to multiple bodies, it becomes an n-body simulation. Modern computers have made n-body simulations powerful tools for predicting planetary motions far into the future, or simulating complex scenarios like galaxy formation. However, before computers, these calculations were done manually, often requiring extensive human effort. Despite these methods, approximate solutions, and labor-intensive numerical integrations, physicists and mathematicians have long sought exact analytic solutions to the three-body problem. Some successes include Leonard Euler's discovery of solutions where three bodies remain in a straight line around a common center of mass, and Joseph Louis Lagrange's findings of solutions where three bodies form an equilateral triangle. These solutions define 5 specific orbits for a third body orbiting 2 others, known as Lagrange points. Objects placed at Lagrange points maintain stable positions relative to the primary bodies, such as spacecraft parked in orbit around Earth. These solutions represent the only exact analytic solutions to the three-body problem known today, inspiring ongoing exploration and application in celestial mechanics. After Leonard Euler and Joseph Louis Lagrange, the search for new specialized solutions to the three-body problem faced a challenge. Exploring the vast space of possible orbits required the computational power of computers. The goal was to find three-body systems exhibiting periodic motion, where configurations evolve back to their starting points, sometimes in complex ways. In the 1970s, Michel Henon and Roger Brauch discovered a series of solutions involving two masses oscillating around the center of mass of a third body's orbit. Later, in the 1990s, Chris Moore identified a stable figure-8 orbit involving 3 equal masses. In conclusion, the three-body issue has been tackled from a variety of perspectives throughout history, yielding approximations that are extremely helpful in celestial navigation practice, as well as theoretically complete but impractical solutions.